Hello, very wonderful people. Welcome to Cosmology Talks and Cosmology from Home, the two best sources of cosmology goodness on the internet. Today is a special talk, as it is both a Cosmology Talks talk and a Cosmology from Home conference plenary. So, welcome both audiences. The topic is super exciting. It's about these pesky, very high redshift galaxies detected by JWST and what implications they may or may not have for cosmology. The speakers are Lilan Yang, who is a postdoc at Kavli IPMU, and Mike Boylan-Kolchin, who is an associate professor at the University of Texas at Austin. Mike and Lilan are the perfect people to speak on this topic. Mike is one of the cosmologists who's been pioneering the idea of using these high redshift galaxies to think about cosmology, and Lilan is one of the astronomers who's actually out there finding them. So we've brought them together to tell us both about how the galaxies are found and what we might learn from them. We're also really lucky in this video because there's a fourth person present. That's Elisa Ferreira, who's an assistant professor at Kavli IPMU. But much more prestigiously, she's also a Cosmology from Home organizer. In the video, Elisa plays the same role I usually play, jumping in with questions and thoughts when something catches her attention. If you like this experiment of having a second guest interviewer, give the video a thumbs up and we can do it more often. Anyway, enough from me. Here are Lilan and Mike.
Hi, thanks for having me here. Today is with Mike. We're gonna tell you what's JWST telling us about the early galaxy formation and also cosmology. I believe that almost everyone has this question when they were kids. At least I always ask my mom well, where am I came from? And she told me that all the kids came from the watermelon. I trusted that when I was young, but now I know that's not true. Now I know our human being appear on the earth around 1.5 million years ago, and our earth is there around 4.5 million years ago, and the timeline of the life probably start at the Big Bang, and the diversity of life on the earth today is really the result of the universe evolution. So from the astronomer and cosmologist point of view, we describe this in this way. And here I show you the timeline of the universe. Well, from the left to right, you will see the Big Bang and the CMB emission. Also, the universe goes through the dark age and a cosmic dawn, realization, cosmic noon, and now today. So previously, the last decades with Hubble, we really know a lot of history about our universe. And the highest redshift that Hubble can probe is around redshift 11. But what we really need to know more is about this cosmic dawn period, and which is the primary goal of the JWST. And at this period, we really care about those key questions, like what are the first stars and galaxies, and how did the realization occur, and what caused it. And from cosmology point of view, we want to know whether the observed structure is consistent with initial condition, and also whether we need physics beyond the current ΛCDM. So you will hear more about this cosmology part from Mike later. I would like to demonstrate why we need JWST. And here at the left, I show you the wavelength coverage of those three telescopes. And you can see at the left is Hubble. It covers the UV to the near infrared. And the JWST here, it's really a infrared telescope. It's covered to the medium infrared. And because we want to observe the early universe, which means the high Z, so we really need those longer wavelengths coverage. At the right, you also see the speeder is covered even longer wavelengths. So here the wavelength coverage is just one important factor. If we want to do good science, we need the good imaging. And we know the image resolution is proportional to the diameter of the mirror size. So at the right, I show you the mirror size comparison between those three telescopes. And you can really see JWST have very large mirror. So compared to Hubble, it can capture the emission from red galaxies and also provide a much higher resolution imaging. And this example is showing the image comparison of the galaxy cluster SMACS, which is known as one of the first imaging released by JWST. And also here, I also show you the comparison between JWST and the speeder at the similar wavelengths.
What was the purpose of it being infrared? Is it to fill this gap in the spectrum, or is there a different reason why we should focus on infrared? I presume that the technology would mean that even if it did exactly the same wavelength as Hubble, it would still be better than Hubble. But is there other reasons for infrared instead?
Yeah, for infrared, compared to Hubble, we can probe to higher redshift, and compared to Spitzer, we can getting much higher resolution imaging.
Stupid dumb question, but it can probe to higher redshift literally because the same colored galaxies are redder at higher redshift.
Yeah, so there are 4 instruments on board the JWST, and here from the left to right, at the first 2 is the near spect and also the near cam. While the near spect provides the spectroscopy, while the near cam provides the imaging. And here I show you the example of the near cam filters. It's from the 0.6 to 5 micron. Another 2 instruments are MIRI and also NIRIST, and both those instruments will provide the imaging and the spectroscopy data. Okay, now you know the details of the instrument. Let's go through this key question list together. The first question gonna be, what are the first star and galaxies? One of the first look is from our Glass JWST team, and as one of the year as the early release science project, the goal is to show the public the power of the JWST as quick as possible. So for our class team, we are targeting this about 2744, the cluster of galaxies here at the bottom left here. And in the center of the cluster, we have those nearest and the near spec coverage here. And also in the parallel field, we have the near cam coverage as indicated by those red and yellow box. And also this green box show you previously, we also have Hubble data here. We're going to show you what we found in those 2 regions, those parallel field and also in the cluster center. Okay, you might wondering with those imaging data, how did astronomers hunt for those high-Z galaxies? We basically mainly use those 2 techniques. And here shows the 3 galaxies spectral energy distribution. And we found them by this the first is by dropout technique. That means for the galaxy you will see in their SED, a large break occur at around the Lyman limit and the Lyman alpha wavelengths. And at the shorter wavelengths, there is a dropout. All the flux is being absorbed by neutral hydrogen along the line of sight. And also, if you have those filters, you have the data from those filters, you can do SED fitting. It helps us to estimate the galaxy's property, such as their stellar mass, their dust attenuation, such like that. So with those techniques, and with just 4 days analyzed, and we found 2 very bright early galaxies in our parallel field, and one is at 10.5, redshift 10.5, and one is at redshift 12.5. And with the real imaging here, you can really see the dropout for the left galaxy. The dropouts is around 115 a filter, and at the right, the dropout is appear at around 150 band. We can also do SED to get their properties in more details. And we also do the light profile modeling. It tells us the size of these galaxies. Those galaxies are very tiny. As you can see, the size for the first one is just around 0.5 kpc, and for the second one, the size is around 0.12 kpc. It's very tiny. And also in our cluster center field, because we have spectroscopy coverage there, and also because it's a cluster center, so taking benefits of the gravitational lensing effect, we discovered one ultra-faint galaxy here, showing at the left figure here, and also the smaller yellow box showing the spectroscopy coverage. And this galaxy is very faint and very high redshift. A red panel here, you can see its position at the redshift and the magnitude plane. So the spectroscopy at redshift is around 10, and the UV magnitude of this galaxy is around -17. And I want to remind you that we always using this magnitude to describe the luminosity of the galaxy, and this -22 is brighter than the -17. And because this galaxy is a lensed galaxy, that means it's magnified and distorted. So if we want to know the intrinsic property, we need to do source reconstruction of this imaging to obtain their intrinsic properties, as I show here. So for the intrinsic of this source, it's showing at the bottom right panel here. And this is done by the software called Landstruction, developed by myself. And the size of this galaxy is very tiny. It's only around 0.15 kpc.
Why are there no low brightness, low redshift galaxies on this plot? Are they just not interesting so you haven't plotted them, or is there a physical reason why they aren't there?
The main idea is to showing this galaxy discovered now is very faint and at very high Z, and compared to previous what we found. And so you can see here, there's one galaxy here. It's previously high Z galaxy found by Hubble. At this high redshift is bright. And for bright galaxy, it will be more easy to detect them. And for those populations at lower redshift, what we can probe previously by Hubble is at lower redshift and with relative bright.
Maybe I can also add that I think this is one that you've discovered through lensing itself, right? And probably the rest of these galaxies are unlensed galaxies, or are those also lensed galaxies?
They're unlensed.
Right. So this is one where it shows you how much more lensing can get you, that you can really probe, a factor of almost 10 fainter in luminosity. So 2 magnitudes is a little less than a factor of 10.
So is the idea that it could have shown up almost at any redshift, and it just happens to be at redshift almost 10, and there's only one because it's so faint?
Right. So I think these observations aren't sensitive to unlensed galaxies at that luminosity. So you need the lensing to do this, and the lensing will only magnify a very small portion of the sky. So you have to be in a very specific configuration to get this right. So it's sort of getting the one lucky galaxy that pops out here, but that will allow you to get this one very faint galaxy.
And maybe I forgot to emphasize this because this is from lensing, so that's why we can probe to such faint galaxy. And we don't have lots of data point here. It's because for glasses, the first try having the lensed data. So for JWST, we only have that at the early results. We only have those very faint galaxy here.
Okay, but so if we left JWST running for hundreds of years and kind of picked out all of the possible freakish lensing events, of which I guess this is one, in principle there'd be a distribution at lots of redshifts of lots of these stars, and this just happens to be the first one that showed up. Is that a fair summary of?
Yeah.
So Lila, about the photometric redshift for the dropout, can you determine any uncertainty in this redshift, or can you just give a number and then you have to confirm?
No, we could have the uncertainty from SED fading. So it can also say the probability distribution of this Z here, this tiny panel here inside this SED fading. So you can see the probability distribution of this Z. So we have the uncertainty. And uncertainty is mainly from the SED fading. I have shown you 3 cases from our glass team, and this slide shows you the results from another survey called JADE, and it's provided the spectroscopy confirmed few high Z galaxies. And you can see among those galaxies, the highest confirmed redshift is at redshift 17.2, and this galaxy is until now the highest spectroscopy confirmed redshift galaxy. Okay, and I have shown you some results about the first star in the galaxy being found by the JWST. And now let's move to the second question. How did realization occur and what caused it? Here I show you the 2 plots, and the first of this cartoon plot, you can see the light emitted from galaxies, the photon from the galaxy, when they hit the neutral hydrogen, it will make the neutral hydrogen ionized. And of course, the recombination process will also happen in the same time. And correspondingly, like in our universe, you can see at the bottom figure here, among the intergalactic medium is full with the neutral hydrogen. Those tiny points are those stars and the galaxy. When the star form and it's emitting the light to ionize the neutral hydrogen among the intergalactic medium, creating those ionizing bubbles. And those bubbles grow up and finally will merge together. So at the end, when they merge together and finally all the neutral hydrogen have been completely ionized, and our universe become completely transparent, and all the light from the galaxy can be reach us freely. This is the end of the realization. We need to count the ionizing photon from those galaxies, and it depends on those 3 factors as shown here from this formula here from the right to left is show the total UV luminosity density, and also those photon production efficiency, also its escaping rate. The most important part is the UV emission from those galaxies those UV luminosity densities. That's why you always hear the astronomer talking about the UV luminosity function. And here in these panels is showing the previous results from ground-based telescope and also Hubble. And in each panel, it's showing you the number density as a function of magnitude. And with previously Hubble, we already have a lot of knowledge about this luminosity function at high Z from the redshift 6 to redshift 10. And we hope JWST can push our knowledge to higher redshift and also find more high Z galaxies to solidify our understanding. So knowing the importance of UV luminosity function, if we try to determine the shape of luminosity function, it's important to correcting the selection bias. And there are two important selection bias. One is due to the brightness and another due to the size. So at the left, I show you here, like in real observation, can say the x-axis is distance and the y-axis is luminosity. And we rarely preferentially detect those very bright galaxies, even we go to longer distance. Well, at the right figure, it shows you like at a given luminosity, we are preferentially to detect those smaller galaxies because it's well corresponding to the higher surface brightness. That's why when we observe the one luminosity function, we need to correcting those selection bias. So to get that intrinsic distribution as indicated by the red line here.
Can I ask another kind of stupid question about infrared? I guess this is the UV luminosity function as emitted by the galaxy, which is of course by the time we observe it here pushed into the red, but it's still the UV end of the spectrum. Is that a fair summary of the state?
Yeah. So for the UV, the analyzing photon is really from the UV rather than like go to longer wavelengths, because it's corresponding to the exactly energy can analyze the neutral hydrogen. That's why we care about UV. So with JWST, our knowledge about UV luminosity function is updated, and in one of the latest work, they selected like 23 galaxies using those dropout technique from a few different JWST observations, and those selected galaxies span a redshift around 9 to 17, and indicated by the red point here. And as a comparison, they also show the previous HST selected high Z galaxies. And with this data point, they draw the UV luminosity function from redshift 9 to redshift 16. Well, at redshift 9, you can see the red data point from their work, and this orange data point is from another two independent work using JWST data, while the gray data point is from previously Hubble or ground-based telescope. And also the red line here is showing their fitting results using two slightly different models. So at redshift 9, with JWST, it's showing the consistent results with previous Hubble. And because they have this data point at higher redshift, so you can see they also deliver the results at redshift 16. But the data point there is still limited, and so the current result is still uncertain. But with future observation, I believe that we're going to have more and more data points at higher redshift to solidify our understanding.
And in that plot, what was the red line and the red band around it? And the dotted red line as well?
The red line is their fitting result.
To some model?
They model the luminosity function as a Schechter function or like a double power law. So they're slightly different. As mentioned before, the size and its relation with luminosity is important to determine the shape of luminosity function. And here I also show you the JWST updates of the size luminosity. And from the upper left to bottom right is showing the size luminosity function from the red frame optical to the red frame UV. And with JWST, it's the first time we can have this observation at the red frame optical. And the solid line each panel showing its fitting result. And at the bottom panel is showing the comparison with previous Hubble results. You can see like in terms of size luminosity, we also found consistent results with Hubble.
The dashed red line in the everything except the top left-hand line is the equivalent of the red line in the top left-hand one, is that right? And it's just extended, or?
Oh, the red line here is showing the results from the red frame optical.
So the solid line in the top left-hand plot becomes the dashed red line everywhere else to compare to the other observations. Is that right? Okay, cool. And so the interpretation is that, the dashed red line is going through the other data points despite being fit to the F444W1. Is that right?
The red line is the solid line, the fitting result, and the dashed red line in each panel is the fitting result from 444 band. So to show that as a comparison to other bands. With all those data, we can do this one-to-one size comparison between those rest frame optical and short wavelengths. As shown here, the x-axis size is from rest frame optical, y-axis size is from other short wavelengths data point. And from this plot, we can see for those galaxies, the median size is around 0.5 kpc, and also the size does not vary significantly as a function of wavelengths. So I will show you the updates of the relative bright galaxies for both luminosity function and size luminosity. I mean bright, I mean like their UV magnitude is brighter than -18. But there are also significant contribution from faint galaxies. But faint galaxies is difficult to observe directly, so that's why we need gravitational lensing help us to probe that. So here I show you the results at redshift from 7 to 9, the red point from the Hubble lens galaxy observation, and the very faint galaxies is fainter than -18 and even reaching -14 or -12. So at the faint end, to determine the shape of the luminosity function, the size and its relation with luminosity is extremely important. And here I show you the size luminosity of those lens galaxy and a comparison with the results from the size luminosity from the bright galaxies. So the colorful line here represents the size luminosity of the lens galaxy, while the black line here shows the relation fitted from the relative bright galaxies. So with a comparison, you can see, like for faint galaxies, the size is very small compared to the relation extrapolated from bright end. What does that mean? That means if in the UV luminosity function, if the size for faint galaxies is very small, then the faint end luminosity function will be flat compared to if their size is much larger. So here is a good summary plot from the recent work. It's summary the UV luminosity function from both like previous Hubble results and the recently JWST results. Now you can see with JWST, we can now push our understanding to redshift 17, and of course the 17 is a photometric redshift, and we still maybe need the spectroscopy confirmation later. And this is only 1 year observation, and I believe in the future JWST will provide us more data points to solidify these results at high Z. And also we know, like compared to Hubble, JWST found a consistent result. And one missing part from JWST is at the faint end, we still now only have enough data from the previous Hubble lens galaxy, and we are waiting for JWST to tell us more also about the faint end.
The blue data point in this bottom right-hand corner is an actual measurement of the UV magnitude, but only an upper bound on
the number density.
Right. Okay. And so you just have an upper bound on the number density. Is that from a lack of observation of?
Yeah, it's because of lack of observation. Going to very high Z, like even now with JWST, because it's only 1 year observation, so the data point is still limited.
And I guess it's just one photometric candidate, so that there's at most this, but it could be nothing, and so that's why there's a down arrow that says that's the upper limit that it basically has. So it's probably a Poisson error on one, and if that galaxy turns out not to be spectroscopically confirmed, then that point can move down to 0.
I see, but it had an actual UV magnitude.
That's right. So in this survey volume, they found one such object, and so that allows them to put one data point with an upper limit basically there.
A quick question. So if it is confirmed, the way I could interpret this is that it's really far away from the curves where it was expected to be at redshift 17.
Absolutely.
Yeah, so for the modal part, yeah, those lines show in the different modal prediction, like they are using the different cloud formation model. So that's why they give different lines.
And I think you can see already at, say, Redshift 12, 13, 16, that the data points are, if anything, lying high compared to most models and maybe compared to all models. So this is some hints that there's more star formation at early times, but we need more data, of course.
So JWST is going to give us more on high redshift, but also on the fainter end.
Yeah. So the faint end will from like the deeper observation and also lensing data.
And none of the ones we're seeing at Redshift 13 are the confirmed one, right? The spectroscopy confirmed one.
Yeah.
So we need to wait.
Yeah, we still need to wait. We already we still remember that with Hubble, the highest what we can probe is only at 11. So basically, previous Hubble we only have knowledge lower than around 10. And now we already can go further away. It's just because of the time, so we need to wait.
What are we waiting for to spectroscopically confirm them? What telescope, what device is the thing that we need for that?
So we have two things for imaging part. We have more large data. Although we only have imaging, but we can do better SED, and we can add more data point in this plot. And the other is because the JWST also have the provide the spectroscopy. So if we can observe the spectroscopy of all those high Z candidates, that would be great. But as we all know, spectroscopy is expensive, much more expensive than imaging, and it's less efficient.
When you say expensive, you mean you have to apply for telescope time and to point it at this galaxy, and everyone wants to be using JWST all the time for all sorts of things, so you just have to wait your turn? Is that what you mean? Or
I mean, for spectroscopy observation, for the one time, you maybe only get one field of view, you only get, 10 to 50 spectroscopy. But within imaging, at the one shot, you can have hundreds of galaxies, which is much more efficient.
And I think also for the same exposure time, you get less in the way of observation for the spectroscopy. So especially for the faintest sources, you just have to sit on them for an enormous amount of time if you want to confirm them. And like Lilan's saying, you need to know where they are sometimes to do the spectroscopy. So it's easy to take the picture and then you have to go back and do the imaging unless you are already doing it you have the ability to go back. You have to apply for the time to go back.
And JWST doesn't have any half-life or anything, right? It doesn't have a coolant that's going to expire. So if we just wait long enough, someone will eventually do this? Or is there some reason why JWST stops working after X years? Or
yeah, it has fuel that it needs to stay positioned and various other things. So it was planned for a lifetime of minimum of 5 years, and they were hoping it would be double that, so 10. But now the amount of fuel it took to get to its final position, they're expecting maybe it can last double that or even longer. So we're thinking for a long mission, hopefully.
So this is a summary plot of those luminosity function. And I think now I have told you the first two questions in the key question list. And now it's time for Mike to tell you more story about the last two questions.
Okay, well, thanks very much. I think that was a great overview and a great lead-in to the questions that I think we can ask from the cosmology side, which is, are the observed structures that we see consistent with the initial conditions of the universe as we know them? And do we require potentially physics beyond our base 6-parameter flat lambda CDM model? And I think it's really helpful that Lilan ended at the idea of luminosity functions, because sort of counting the number of observable galaxies as a function of some observable property, be it rest frame UV luminosity or stellar mass per unit volume, maps in some potentially complicated way into the observable that cosmologists want to know, which is the underlying mass density field. And of course, we have a good understanding of that theoretically from observations of the microwave background. The temperature fluctuations are of order apart in 100,000 at redshift 1090, and that for a 6-parameter lambda CDM model gives us everything we need to know to tell you about the statistical distribution of matter and its evolution throughout the rest of the history of the universe. So we know how to understand the structure at very early times and how it can move into later times. And so that is in some ways done with linear theory. So if you take a map of the CMB and understand what it requires in terms of components of the universe. You can then do a statistical realization of this. And at redshift 127, let's say, everything is still well in the linear regime. And so you might find something that looks like the density field you see here. And I should say this actually is a real density field from a cosmological simulation. This is the well-known Illustris simulation. But you don't even have to stop there if you don't want. You can also do a linear extrapolation to the present day. So this is what, if you just use linear theory, the matter density field should look like today. And so we have all the tools to do this sort of completely, with complete knowledge based on our cosmology. So once you say, here are the energy components of the universe, dark matter, dark energy, baryons, and you say, this is what the power spectrum looks like, and you specify the angular size of the sound horizon and the optical depth, the last scattering, this uniquely specifies the matter density and its evolution in linear theory to the present day. Right, so but we can take that then and actually use models like extended pressure theory to predict the abundance of nonlinear peaks in the density field. And so that's the key that we want to do here. We want to go from this linear density field to understand the nonlinear density field, the density field that gives birth to the galaxies we see around us. And so this number density of dark matter halos, of collapsed objects in that density field, is the key connection to those observables that Lilan was talking about, to that galaxy luminosity function, because dark matter halos are what hold galaxies. And so in some way, this dark matter halo mass function, so what's plotted here is a cumulative mass function, the number of dark matter halos above a given halo mass per unit volume. And that maps on to the co-moving number density of baryons as well that are in those dark matter halos. And that can be seen in the upper axis of that plot. So that tells you how many baryons are available in that given halo mass, assuming everything has its cosmic fraction of baryons. So what we'd like to do is now understand this mapping, well, either the forward mapping from a cosmologist point of view of the halos to the galaxies, or the backwards mapping from the point of view of an observer who observes the galaxies and wants to get at the halos maybe. And this is sort of the plot we saw earlier. We want to understand how do we go from a number per unit magnitude per volume to a number per unit dark matter halo per unit volume. And so there are very good ways to do this, okay? And actually, it can make it look very simple. So just a straightforward equation. If you know the dark matter halo mass function, then you can get the galaxy UV luminosity function. So what you do, you want to get this UV luminosity function, and you say it's just an integral over the dark matter halo mass function times a probability that a halo at a given mass hosts a galaxy with a given UV magnitude. Okay, and so this looks nice and simple because it's just one integral, but this is not so simple in practice probably, right? This is where all of the messy stuff could potentially be. But this is really how one can do it. If you have a model for given a halo mass, what is the probability that you have a given UV luminosity, or equivalently a given stellar mass, you can map from this halo model to the galaxy observable, the UV luminosity function, or the UV stellar mass, or the stellar mass function of galaxies. The key here is that this galaxy formation physics could be complicated. The UV luminosity is very closely related to the star formation rate, and the reason for that is that the UV light of a galaxy is dominated by hot, young, massive stars, and that's why we're sort of looking at this rest frame UV that's showing us the recent star formation in these galaxies. So the star formation rate in this kind of model is, again, deceptively simple. It's just some function of redshift and halo mass times your cosmic allotment of baryons, the cosmic baryon fraction FB, times how fast dark matter halo mass is growing, right? So you're basically saying the stellar mass is equal to the accretion rate, now scaled to the baryon accretion rate. That's why we have this baryon fraction, and then some conversion efficiency of those baryons into stars. And again, this F star is all of the complicated business of galaxy formation there. So, but you can make simple models, right? You can basically say, is this conversion efficiency constant across time or across redshift equivalently? and just depend on halo mass, let's say. There are models. This shows you how much star formation rate there is per unit volume as a function of redshift. This is the famous cosmic star formation rate density. And as you go from left to right, you're going from the present day back to earlier times. And this is sort of the pre-JWST state of the art. You can see the data points, and the red line is really just taking this CMB cosmology, taking Planck dark matter halo mass function, and saying that those baryons are converted into stars at a constant efficiency as you go back in time. So there are fewer dark matter halos that are massive, and therefore you get fewer stars. There's less star formation. But the assumption here is just that all that matters is the baryons in that halo. It doesn't change with redshift. And that's providing a pretty good fit here, pre-JWST. Now we add on to JWST, okay? We can see what that looked like. So they've changed the color, but the blue dotted line or dashed line in the right plot is the same as the red dashed line in the left plot. You can see the x-axis, the redshift axis, has been extended now. But the data have started to deviate from that line of constant efficiency, and they've started to deviate in the direction of having more star formation than this constant efficiency model would predict. So if we really just say it doesn't matter what time in the universe you are, you always convert a constant fraction of your baryons into stars, that would underpredict the amount of star formation that JWST appears to be seeing in the early universe. There seems to be surprisingly high levels of star formation at high redshifts in these early JWST data.
And what is the Maddow and Dickinson model? That is, I guess, the other extreme that...
Right. So the Maddow and Dickinson model, I think, is integrating much further down the luminosity function. So this would be for, say, all galaxies that you could really see. We're only really seeing sort of the brighter galaxies. So if you could, with JWST, sit for years on this field, you might be able to see fainter and fainter galaxies, and then you get more and more. So the Maddow and Dickinson, I think, is really just saying, well, it was a fit that they did to the even earlier data, but I think that the fit goes down to much fainter galaxies than what we're seeing here with JWST.
So if JWST saw something above the gray line, then there's no astrophysics that would save it. It would be like ΛCDM is wrong, I guess.
Well, I think the gray line isn't sort of an upper limit to ΛCDM. It really is something that they got from fitting the earlier data. So I don't think it's something that we should take as that's violating that will violate ΛCDM. There are constraints you can do on that, and I'll maybe mention that in a minute, but this is not exactly that. Yeah. And just to see it another way, if we zoom in a little bit on this sort of higher redshift region, now the purple line in the left plot is showing this kind of constant star formation efficiency, and the blue line going through the data points, those are several groups that have now analyzed JWST data, and you can see that really, let's say at redshift 13 or so, we're talking about a significant factor in excess of this constant efficiency model. It's a factor of maybe 10 or more in terms of the star formation density. That is, the UV luminosity density is 10 times higher than this constant star formation efficiency model would predict. So that's a big difference than what we might have expected.
And is that blue line just empirical, or has it got some, like, because it fits the data well? If it was a well-motivated model, it feels like that's the right model.
Yeah, so I think that blue line is just a fit to the data. I don't think that that's an empirical model even. I think it really is just really fitting the data, but I should double check that, yeah. So then we can also not just map the UV luminosity density, but with some assumptions about how stars are forming, you can convert that into the stellar mass of these objects. And so some of the most surprising results from the earliest data were that there are very massive galaxies. Now not at the highest redshifts, so not above redshift of 10, but at the redshifts that Hubble has probed, so redshift 7 to 10, but now with this changed wavelength coverage, we're able to infer the stellar masses of these objects differently. And so we're not looking at the UV luminosity density like Hubble was, we're really trying to measure how much mass in stars there is. And so this shows you the log of the stellar mass on the y-axis against redshift, and some points are highlighted from Lebet et al. 6 of these data points lie above 10 to the 10 solar masses in stars, at that time. And just for some context, the Milky Way at the present day is at around 6 times 10 to the 10 solar masses. So at least one of these data points at face value is in excess of the Milky Way's stellar mass at a time that is only, say, 500 or 700 million years after the Big Bang, so 13 billion years ago. So this is pretty surprising. And, we don't exactly know what the Milky Way's main progenitor looked like at these redshifts, but since I'm making the plot, I can put it on here, and a reasonable guess might be something like this, okay? So the Milky Way might have been, certainly well under 1 billion solar masses and stars in terms of the main progenitor, and probably closer to tens of millions. So we're talking about galaxies that are tens of thousands, potentially, of times more massive than the Milky Way's progenitor at this time. So again, a lot more stars than we might have expected. And I'll get into some of the unknowns about these and the caveats.
These guys that we're seeing at a redshift 8, when they become redshift 0, what would their masses be? Would they not have just grown to some enormous thing? Or will they get just torn apart because they're at the center of some huge galaxy cluster?
Well, they definitely shouldn't be torn apart, we think. I mean, they are pretty compact galaxies, so these would probably have to be the centers of the biggest galaxy clusters we see. The potential issue there is that these are seen in a pretty small volume of space, and so the issue is, can you really map this out so that it all works out? So clusters today have a number density of maybe 1 per 10 to the 5 or per 10 to the 6 cubic megaparsecs. This field is of order 10 to the 5 or 10 to the 6 cubic or 10 to the 5 cubic megaparsecs. So it's really pushing the limits of this, which is also maybe asking, is there some uncertainty in this result? And I can get into that in a minute.
Would these guys not have just kind of like merged in some way? Or I guess that's what I meant by torn apart, like just kind of...
They would have merged with other things, but, we know how massive the most massive galaxies are around us today, and it's not growing by the same factor as the Milky Way is growing, certainly, right? The biggest galaxies around us today are maybe 10 to the 12 solar masses and stars, or a little bit more. So this only has room to grow, this biggest data point, by a factor of maybe 10 at the most. Whereas, you can see the Milky Way grew by a factor of 1,000 or more in this case. So we can do sort of the equivalent of looking at the star formation rate density and ask, what is the cumulative stellar mass density in these systems? So how much mass in stars is there per unit volume in galaxies more massive than the value on the x-axis? Okay, so this is just asking per unit volume of space, how many stars are there in these massive galaxies? And you can see what the extrapolations are from Hubble results at redshift 8 in the purple and redshift 9 in the red. And these JWST results, the early ones, are significantly above both of those. So this is, again, from Lebet et al., saying, I think, consistently with this picture of high star formation rate density at early times, there seems to be a lot of stellar mass buildup in these massive galaxies. But now this gets at Shaun's question about, is it possible to do this in ΛCDM? And the problem turns out to be, you can just take the dark matter halo density field again and say, if we ask about all of the baryons that are available and we convert those baryons into stars, do we have enough baryons to make these stars that we're seeing in these galaxies? And you're really right up at the edge of what is possible. The black line is the maximum possible given the Planck cosmology for a typical volume of the universe. And what you can see is some of these data points are right there. And the other lines are different star formation efficiencies, so what fraction of baryons are converted into stars. We typically think of 0.1 or 10% as being kind of an upper limit as what we see. And so these are all well in excess of that for the assumptions that have been made. So if everything is as these observations are saying, then these are really incredibly efficiently converting baryons into stars, and maybe too efficiently given the cosmology that we have today. And just to give some kind of numbers for people who think in cosmology terms, we can think of sort of the peak height in the density field, so how rare is this object? The y-axis here is the stellar mass, or some conversion efficiency times the baryonic mass. The x-axis is the redshift. And these are two of the most massive data points from Lebet et al. So even if we assume 100% star formation efficiency, 100% of the baryons are converted into stars, they sit in sort of 4.5 sigma peaks, which would correspond to galaxy clusters, again, that are today of order 10 to the 15 or more than 10 to the 15 solar masses. And if the conversion efficiency is lower, they're in even rarer peaks because you need more massive dark matter halos to provide that much stellar mass. You need a bigger baryonic reservoir. So that would mean they'd have to be incredibly rare objects. And again, these have been found in a very small region of sky, 38 square arc minutes, so less than a millionth of the full night sky.
This epsilon equals 1, I was going to ask a question saying that must be very conservative, because if epsilon equaled 1 at that high redshift, there'd be no stars at our low redshift because they'd have all of the baryons would have been used up. But I guess these are the most extreme objects, so if epsilon did happen to be 1 for these, the rest of the universe at redshift 8 might have a lower epsilon, so there's still gas around to make stars later on. Is that?
Yeah, that's right. So it really is, for the most massive systems, they would have had to burn through all of their fuel supply, but they will get more gas falling into them, right? And there are lower mass dark matter halos, you're right, and they could have different efficiencies potentially. But it's hard to see. I mean, these would have been lower mass halos at earlier times, so it's a little strange at some level. And, so it may be that, that these are coming out of early data releases and people have vetted these very well, but there are certainly questions that I'll get into. But just to give you a sense that these aren't maybe particularly it's not outrageous to think such things could exist. I want to show there is an HST plus ALMA detected galaxy, so a spectroscopically confirmed system, just at slightly lower redshift, even higher stellar mass, incredibly large black hole, already 10 to the 9 solar masses, so a billion solar mass black hole, an incredibly high star formation rate of over 1,000 solar masses per year. And so this is, again, an extreme system, but just to say they're out there. And so maybe it's not impossible that some of these systems that are being seen with JWST are similar type objects. And just to show you again, with other observatories like ALMA, you can find these very dusty, massive galaxies at early times. Same kind of idea. Okay, so I think maybe more excitingly, what could be going on here? So I think there are lots of possible explanations within the standard cosmology. So there are lots of possibilities, including, we need to map from the observed light to the underlying stellar mass, and that's complicated. If there's an AGN contribution, if a black hole is contributing to the light that you're seeing and you don't model that correctly, then you'll overestimate the stellar mass of the galaxy. You have to try to understand how the stars have been formed over cosmic history, and if you don't do that right, you'll get the wrong stellar mass for the galaxy. And you also have to assume how stars form as a function of mass. Are there lots of high mass stars, which are also the bright stars, or is most of the mass in low mass stars, which don't contribute much of the UV flux? And so if it turns out that the stellar initial mass function is different at high redshift than at low redshift, then again, these masses could have been overestimated, and that would ease this tension. So there are lots of ways this could not be sort of a contradiction with ΛCDM. The other one is that it's possible that just looking at different parts of the sky gives you not sort of the cosmic average, but since you're looking at a very small region, you've got sample variance, and we just happen to look at a part of the sky that has some massive galaxies. Now, the other possibility is that this is telling us something about cosmology, and so I thought I'd walk through a couple of the things that people have talked about on this side, just to give you a sense of where things need to go. So if it is a cosmological issue, what you really need is more or faster formation of cosmological structure at early times. And within that base 6-parameter Planck ΛCDM model, there's no way to do this. There's no wiggle room. All of the parameters are known to a high enough precision that you can't just fudge this around a little bit and get more galaxies at early times. But what you can do is say, well, this is just a model, and we have to say that we understand all of the energy components of the universe. If there are other energy components that haven't been modeled here, then maybe we could get this to work. And what you need is something that has a higher density of matter, a higher amplitude of fluctuations, or a steeper spectral slope, so there's more fluctuations on galaxy scales relative to the CMB scales where we really measure them well. And so one such modification potentially is called early dark energy. it's a very weird model, but bear with me. So you just have a fractional energy density contribution of 10% at around the redshift of matter radiation equality. And then this field decays away. So it's only a very brief period of time, 50,000 years after the Big Bang, where this matters. But the universe expands a little bit faster, it cools a little bit faster, recombination happens a little bit earlier. And to compensate for that, to match the CMB, you need to add more dark matter to your model. So you refit everything, and you say to compensate for this extra early dark energy, you need also extra dark matter to still fit the CMB. So that's a possibility, and if you do that, you can ask how many more galaxies would we expect to see in early dark energy cosmologies versus Planck cosmologies. And this plot shows at a variety of redshifts the ratio of early dark energy number densities relative to Planck number densities. The leftmost blue curve is at redshift 15, moving all the way down to the right, the yellow curve is at redshift 1. So what you can see is that at early times and low halo masses, you can really get to number densities that are 5, 10, even 20 times larger in this early dark energy cosmology compared to Planck. And again, that's because we're probing an exponential tail of this density field. And so a slight change in the overall matter density or the parameters can lead to an exponentially larger number of objects. And I've also shown here sort of the number you'd expect for fields of various surveys that are out there. So the Sears survey is where these first galaxies were found. Those are the stars. Cosmos Web, I think Lilan will talk about briefly, is a much wider survey, so it can see much more in the way of the universe, and that can see maybe a factor of 2 lower number densities, so more galaxies there. So if we can look at this, we can maybe discern, but it really does require going to lower stellar masses and earlier times cosmologically.
Is it worth pausing to point out that these early dark energy models became popular because they do, to some extent, alleviate the Hubble tension as well? And then do you have insight onto whether the parameter ranges are kind of consistent between the two uses of these models, or are they completely different regions of that model?
That's exactly right. So these were originally proposed for the Hubble tension. I should have said that at the jump, and that's the only reason I think one would really consider these seriously. If it was just a few massive galaxies at early times, it would be hard to do this. But if you now have sort of one tooth theory that explains two things, that's better than two tooth theories to explain those two things. So that's maybe worth taking it seriously. And it seems like if one is just considering the Hubble constant and these galaxy number densities, that the parameter space is the same. Now there's questions about the S8 tension and various other things when you're doing these kind of models. I think that those are lower level tensions than the Hubble tension at this point, but it's worth exploring whether, can you thread that needle? And it's not obvious that you can, I'd say. The other possibility is that we really don't know the power spectrum at large wave numbers or low masses very well. So really, we sort of don't know if there's new physics here at sort of K of 10 or 100, certainly. So for example, if there's warm dark matter, this will cut off that power spectrum, and that could be reflected in the number density of galaxies, because that would change the underlying dark matter halo mass function, which would change where the galaxies could form. So this is just to show that if you do this for expected results from JWST, you can start to find that CDM, which is in black, and gives you a very different result from warm dark matter, which is the sort of blue and red points. And so maybe this will give you a constraint that it could be mapped onto these JWST luminosity functions. So that'll be important moving forward. I don't think we're at very strong constraints right now, but you can see that it's very hard to accommodate a 1.5 keV warm dark matter model with the data already. Now, I think there's other reasons that's ruled out, but you could imagine that pushing to fainter limits will improve these exclusions.
But the data here is consistently below the models everywhere, right? So what is going on there?
Well, it's not below the models at the lowest masses at, say, redshift 9, right? Or 6, 7, 8. Well, 8 is the one, but at redshift 6, 7, 9, the purple triangles are all above the red. And so that says that there's no way you can have the 1.5 keV warm dark matter model be consistent with that observed luminosity function.
Why shouldn't they be on the data? Like why is, like, I mean, at mass 10 it's below all three lines.
It's not a problem to predict fewer galaxies in the lines. It's sort of a threshold thing, right? You don't want to predict more galaxies in there, but you can, because you can move these lines over by changing the galaxy formation. But if you already predict more galaxies than there are dark matter halos, then you've got a problem.
And how are those lines calculated? Is this from simulation or?
So these are, again, assuming some kind of constant conversion efficiency of baryons into stars and using an underlying dark matter halo mass function. And I don't remember offhand which the conversion efficiency was for this one, but probably a high one. So the other possibility, the last one I wanted to talk about, is that you don't change put a cutoff in the power spectrum, but you could imagine beyond where we've probed things, the power spectrum has a different tilt. So there could be physics that changes that power spectrum at very large K. And so in this paper, they explored either a hard tilted model, so where there's a lot more power, that's the dark blue, or where there's a little more power at large wave numbers, small masses. And what you can see again is that compared to ΛCDM at redshift 9, those tilted models produce a lot more structure. So you're seeing the underlying density field in the top panels, and then the halo masses in these models in the bottom panels. And again, these are the exact same power spectrum on small wave numbers, so large mass scales. It's only changed at these small ones. And you can see it produces an enormous change in the number of dark matter halos. So by probing these galaxies at early times, we're probing the power spectrum at these early times as well, and you can put constraints there. And again, if you try to do this at lower redshift, you see that you don't see any difference whatsoever. That's the bottom plots here. It's really, these differences are erased through time, and that's why we want to look at these high redshifts to try to understand what's going on there. And so I think that the next exciting chapter is to try to get even larger samples of these galaxies so we can really do that. So maybe I'll turn it back over to Lilan, and she can talk a little bit more about what's forthcoming with JWST.
Mike, just getting back to the possibilities to explain the data. If it is galaxy properties, whatever it is, the conversion rate or IMF or anything, can you quantify how weird those would have to be? How different, how possible are they to explain?
That's a great question. I think it is possible to do this, and people are starting to do that. The problem is it's a multi-dimensional parameter space, and so we do understand what it looks like it would take, and it would take significantly more efficient conversion than what we see at low redshift. So maybe this epsilon, instead of maxing out at 10%, might go more like 20 or 30% to explain the star formation rate densities. And there are models for why that might be the case. But again, this wasn't what was predicted ahead of time. The predictions were not looking like that, right? So there is maybe something that's changing in the way stars are forming or the way galaxies are converting gas into stars above redshift of 10 or something like that is what this might be pointing towards.
If these rare galaxies are very far in the tail of the distribution, some kind of non-Gaussianity of the primordial distribution would presumably also have a large impact on these and not on anything else if they're in the tail. Is that something that people have already looked at, or is it just kind of next on the menu?
Yeah, absolutely. So there have been people who have looked at primordial non-Gaussianities as an explanation for this, and that is certainly something one could resort to. And I think that it's important to sort of map out all the possibilities, and then when the data come in, we can really see, do we need to do this? But now at least we understand what the parameter space could be for solving this with changing cosmology. It may just be that it's galaxy formation, probably something to do with galaxies and understanding the observations, but it is worth exploring the cosmological side as well, absolutely. And I think these are some of the rare probes we have of cosmology at early times, and we'll get lots more of it. So it's a worthwhile data set for cosmologists to consider.
Maybe my last question. So there's many possibilities, and obviously we need more data. But is there something that we already learned with this, with what we have now? We already know something, like there's a chance of this or that.
Well, I think what we do know is that there really does seem to be more star formation at early times, and there really seems to be an excess of black holes compared to massive black holes compared to what we thought at early times. So there seems to be more very early star formation and more massive black holes, and sort of understanding these two together is already very exciting, I think, even if we don't break cosmology.
So it's not like just with 1 year's observation, we already found very interesting stuff with JWST, and we found many of those bright and massive high-Z galaxies up to redshift 16 to 17. And that's not the end. We have more. Like this slide show you other underway JWST programs, what helps us to further help us to understanding the galaxy and the cosmology. And you can see like all those programs, they forms as a Wending Cape structure, like for a very large program, the Cosmos Web, like it's very large, shows this relative center. So then the very, very deep survey, the NG deep here, like this is relative small, but it's going to very deep. So it's also will help us to like observe more those faint and no massive galaxies at high Z, which is still missing using JWST. So I will give you more details about the Cosmos Web, and it's the biggest survey. And our Cosmos Web, our team, like the field of view, you can see the comparison with the full moon. The field of view size almost 3 times of the full moon. It's a very large area, and we're supposed to discover like thousands of those galaxies at very high Z, like from larger than redshift 6. It will really solid our understanding even for those very bright galaxies. And here's the summary plot. I think we go through our key questions. And for the first two, I think I tell you like now we can go to like a redshift at 16, 17, but with the highest spectroscopy confirmed redshift is still at 13, and we are looking forward push that to higher redshift. And also as the light from the galaxies like is the source for ionization, and we know the UV luminosity function can tell us the number density of those galaxies, and we already have more knowledge at the bright end, but we still need more like go to the faint end. Then it's about cosmology. Mike, you can give a more summary.
We talked a lot about this, but really this ability to probe the underlying mass density field with these galaxies, potentially probing the rare objects and regimes where we haven't looked before, gives us a really nice way to look at certain aspects of this cosmology that we're just not able to look at otherwise. We can make certain assumptions and know how to go from galaxies to mass or mass to galaxies, and that can teach us about what's going on there. So from some of the things that Lilan has talked about, we know that star formation is more efficient at early times, but does that say even that's not enough to explain the observations? Do we need something even further? Can these observations really reveal the need to go beyond this 6-parameter ΛCDM? So I see this as a great way to test our initial conditions from the CMB to some of the earliest and rarest galaxies that maybe JWST can see at these early cosmic epochs. And so I think it's really an exciting time for both the galaxies and the cosmology side.
Is it right definitely to say that the scales probed by these galaxies at high redshifts is much lower than anything probed by the CMB? So the connection is purely because in ΛCDM the primordial power spectrum is only given by 2 parameters, which, okay, maybe is true and fits stuff like inflation quite well, but in principle they're not constraining the same scales. Is that?
Yeah, that's right. So if you sort of want to think about a mass fluctuation as being, this mass as being the mass contained within a given radius, the radius that corresponds to the size of the sound horizon in the CMB, which is that, peak at L is 300, or the acoustic scale is L of 300, might be 10 to the 18 solar masses. And so L of 3000 might be 10 to the 15 solar masses. So this 10 to the 12, the right edge of this bottom plot, would be a peak scale of 30,000 in the CMB. And, as you get down towards the left end of this, we're talking about a scale of 300,000 in the CMB. So that's really much further out than at least Planck is probing in the CMB. And it's very, very hard to get much information out of primary anisotropies since they're damped so much there.
Okay, so this is just the early release, right? So which went, from what I'm understanding, went above and beyond what was expected. So I would like to know from Lilan and Mike, what are you guys personally expecting? What is the timeline? And also in the end, maybe Mike, what would you ask for observational people like Lilan? What is your wish list for them? And maybe Lilan, since the audience is most cosmologists, what did you tell cosmologists with regards to the future of JWST?
The first thing I think I'm looking forward, my personal wish list, I think I wish for both bright end and faint end, I wish JWST can provide more like bright galaxies in high Z to solid our understanding about the bright galaxies, to figure out whether like it's possible that's what's happening, why we can observe those very massive monsters at the very beginning, very early universe. And also, in another hand, I also hope JWST can observe more faint galaxies, because there are actually a large amount of faint galaxies that we haven't observed yet, like with deep survey or with help of gravitational lensing. And then for cosmologists, I hope cosmology can tell me like more model to help me give a constraint like about whether it's possible I can observe such high massive galaxy as that early universe, whether there's something wrong, I made a mistake in my calculation, or I probably missed some parts of the unknown new physics.
And I'm really excited to see the next set of observations where, as you said, Elisa, it's sort of this early data. There's a lot of it, and there's a lot of great data, but really building up the statistics and understanding this kind of comprehensive picture from the earliest times we can measure with statistical rigor to bigger volumes, more objects, and really trying to make these statements precise, not just sort of saying, wow, it looks like there's more of this here than we expected. How much more, what level is this a problem? And then given things like the Hubble tension, should we be thinking that this is something that needs to make us think about the cosmology and potential changes? Or is it something that's really reaffirming the cosmology and we really need to understand how galaxies are forming? And I think that's something that cosmologists are always wondering, right? We want to break the model at some level, but we'd also really like to know if it's really just ΛCDM, what does that mean for how we make a predictive theory of galaxies forming from the earliest times to the later times. And so observationally, I'm really excited to see the sort of complementary, much bigger surveys like Cosmos Web that Lilan was talking about, and then the much deeper surveys that are going to go much fainter. And I think the other thing that's exciting is, the highest redshift results get the most news, but there will be fantastic data at what used to be high redshift. At the end of reionization, redshift 6 will really go very faint. We'll be able to understand metallicities, oxygen abundances, how stars are forming, and really try to connect up to these surprisingly massive black holes maybe. Is there something interesting and exciting about the formation and evolution of these black holes? Can we learn about the seeds of these black holes, or will it tell us about whether they form from stellar processes or direct collapse of gas, and what's going on there? It may be very hard to figure that out otherwise. And so I think the next set of data from JWST, we're really talking about time scale of year-ish or a couple of years, not something like 30 years to figure this out, which I think is nice for somebody who may not be doing cosmology in 30 years from now. Yeah.
Awesome. If you liked that video, don't forget to subscribe and click like to help with YouTube algorithms, both for yourself and for the channel, because YouTube will know to recommend more stuff like this to you. Click the bell to be notified of new videos. And if you're at Cosmology from home, go ask some questions in the Mattermost. Other than that, thanks Lilan and Mike for the great talk.
Yeah, thanks.
Thank you very much for having us. I really enjoyed this.